Hello, and welcome to the video accompaniment to Chapter 1, Section 3 and 4 of our text. In this video, we're talking about implications. In order to understand implications, we'll need to be able to recognize an implication. We'll need to be able to tell when an implication is true or when it's false. We'll need to investigate how the converse and the contrapositive relate to the original implication. We'll need to be able to negate an implication. We'll have to understand this related concept of a biconditional and be able to tell when that's true or false. So we'll look at these in this video. If you haven't yet already, make sure you read through the chapter, read through these sections, and make sure you're familiar with any definitions, and make sure you go through a few examples on your own. All right, let's get started. In order to understand implications, we first just need to be able to recognize when we're dealing with an implication or not. So for this, let's just look at an example. Consider the following statement: if you cross the Mackinac Bridge, then you pay $5. So the fact that we're dealing with these words if and then, these are sort of keywords to tell you that we're dealing with an implication. If this condition is satisfied, you cross the Mackinac Bridge, so I'm going to call this P. And then this other condition has to be satisfied. You pay $5, I'll call that Q. Now you might think of you cross the Mackinac Bridge or you pay $5 as open sentences with you being the variable, but in this case I'm going to think of them as statements where the variable for you is you, the listener. So I'll think of you as you, and so it's a particular value there. So I'll think of these as statements. So some terminology that goes along with this, right, is that P, this here is the hypothesis. So that's another way to say this is the hypothesis. And then Q is the conclusion. If P is true, then Q must follow. This is why it's an implication. All right, so this can be stated a lot of different ways, and sometimes without using if and then. If and then is sort of the standard way to say it. But we don't need to. And actually, first let me just write out notation-wise how we could define this thing. So with P and Q defined as I did, this would be P implies Q. Right, so how else can I state this implication, the same implication? Well, I could say something like, you cross the Mackinac Bridge only if you pay $5. Right? The Mackinac Bridge is a toll road. This implication is true. Anytime you cross the Mackinac Bridge, it follows that you have to pay $5. Another way to say that is that you cross the Mackinac Bridge only if you pay $5. So it's an equivalent way to say it. You also might hear Q if P. So you pay $5 if you cross the Mackinac Bridge. It means the exact same thing. Still telling me the same thing, that this conclusion Q follows from the hypothesis P. You might also see P implies Q, and I've actually already used this already, right? You cross the Mackinac Bridge, that condition implies that you pay $5, that condition. And then these last two, we use the terms sufficient and necessary, and these are going to crop up a lot later on, these terms. They'll be useful for just talking about these implications. And so let's look at that. So what this P is sufficient for Q is saying is that the condition P suffices, it's enough in order for the condition Q to be true. So as long as P is true, then Q is true. That's what the sufficient means. Necessary is a little bit different. Notice we've flip-flopped the P and the Q here, that Q is a necessary condition for P. So you paying $5 is necessary in order to cross the Mackinac Bridge. So Q is necessary for P. So all these different ways of saying it are the same. They're all stating the same implication, P implies Q. Cross the Mackinac Bridge, then you pay $5. One concept I've seen students struggle with in the past is understanding this definition for implication in terms of the truth table. So really what we're talking about here is just being able to see what the truth value of an implication should be. So for this, we'll first just look at the definition of an implication. We'll let P and Q be statements, and we'll look at the definition in terms of a truth table. So here I'll list all the different possibilities. truth values of P and Q, anything that might happen. Lastly, false, false. So P implies Q is defined like this. And it should make sense. It might be a little bit weird, but it does make sense just colloquially, thinking back to maybe that last example. So P implies Q. That means every time P is true, Q must also be true. So if P is true and Q is true, okay, that means this is true. The implication is true in this case. In this next row, the hypothesis is satisfied. P is true, but the conclusion does not follow. And so the implication would be false here. It's not true that P implies Q there. And then these last two rows are really the source of the confusion. Remember what this implication is saying. It's saying if P is true, then Q has to be true. Right? Q follows from P. If P isn't satisfied, if the hypothesis is not satisfied, it doesn't matter what the truth value of Q is. In both of these cases, we still consider the implication to be true. It's still true that if P is true, then Q is true. Right, so I understand why this is a little bit confusing, so it's helpful to go through a little example using words for this. So I'll go back to the if you cross the Mackinac Bridge, then you pay $5. So think about when should we consider this to be true. We know this is a true statement because the Mackinac Bridge is a toll road. So consider what this is saying. If you cross the Mackinac Bridge, then you pay $5. If you don't cross the Mackinac Bridge, it doesn't matter if you pay $5 or not. Mackinac Bridge is still a toll road, and this statement is still true, right? P implies Q is still going to be true in that case, even if you don't cross the Mackinac Bridge. And in fact, if you never cross the Mackinac Bridge, then this implication is definitely true. Remember that saying this, if you cross the Mackinac Bridge, then you pay $5, right? If I pay $5, it doesn't necessarily follow that I have to cross the Mackinac Bridge. All right, so let's look at a more mathy example. For an integer x, consider the following open sentence. So our domain is integers. If x is even, then x squared is even. So when should we consider this to be true? Let's determine all those integers x for which this implication is true. So let's just try a few. Let's try r of 1 would be the statement if 1 is even, then 1 squared, 1 is even. And so this one, I know it's a bit weird, right? But this is true. If 1 is even, then 1 is even. That's a true statement. Let's look at another one. R of 3. If 3 is even, then 9 is even, 3 squared. This one is also true because the hypothesis is not satisfied. So it doesn't matter if the conclusion is true or not. The implication will be true, right? 3 is even, that's false. 9 is even, that's also false. And so that's this last row of the column. This is a true statement. If 3 is even, then 9 is even. Lastly, let's look at a case when the implication is false. Well, we can't actually. This open sentence is true for all integers x. If you have an even integer, then its square will also be even. You can try it with any even integer you want. Maybe let's look at r of 4. If 4 is even, then, so 4 is even, so this is true, then whatever I write over here had better be true. 16 is even. Yep, that works. That would be the first row of the table. True, true. So that's true as well. And we'll actually be able to prove this statement later on, that this is true for all integers x. Right now we'll just say, hopefully it should make sense to you, that no matter what I plug in here, I'll get a true statement. No matter what I plug in for x, I'll get a true statement. And really, we'll see, since if the hypothesis is false, we don't care what the conclusion is. We only really need to consider even integers for this. That's the only thing where any trouble might happen. But if I take an even integer and I square it, the result will also be even. So this is actually true for all x. And like I said, we'll see a proof of that later on in chapter 3. Now there are a few related concepts to an implication, sort of operations on an implication. And that is the converse and contrapositive. So we start with an implication. Let's say it's if x equals 3, then x squared minus 9 equals 0. And so this is an implication involving two open sentences. So I'll maybe call this one P of x equals 3, and Q of x squared minus 9 equals 0. Then this would be the implication P of x implies Q of x. If x equals 3, then x squared minus 9 equals 0. So this is our given implication, has hypothesis x equals 3, conclusion x squared minus 9 equals 0. We can see that this is this implication is true for all x, because if the condition x equals 3 is satisfied, then it follows that, well, the only time that's satisfied is when x is 3, right? And 3 squared minus 9 is 0 in that case. And so this is actually true for all x. Now, along with the implication, we can do some things to it. So the first is the converse of the implication. So given the implication above, the converse is just reordering it. It's switching the hypothesis and the conclusion. So now we have if x squared minus 9 equals 0, then x equals 3. And so Q of x is still x squared minus 9 equals 0. And now P of x equals 3. So notice they've switched locations here. This is the converse. So this is the implication. Q of x implies P of x. And you might think this one's true, but on further analysis we'll see that this is actually false for some values of x. So when x is 3, let's look at this. Let's look at the implication Q of 3 implies P of 3 would be the statement 3 squared, if 3 squared minus 9 equals 0, then we're plugging in 3 for x, then 3 equals 3. So the hypothesis is satisfied, 3 squared minus 9 does equal 0, and the conclusion is satisfied, 3 does equal 3. But let's take a look at another example. How else could Q of x be satisfied? What other value of x makes Q of x true? Well, that would be negative 3. So let's just look at the converse evaluated at negative 3. Q of negative 3 implies P of negative 3. So Q of negative 3, so this is negative 3 squared minus 9 equals 0. I should say if. Then negative 3 equals 3. So again, just plugging in negative 3 for x here. So here the hypothesis is satisfied, right? Negative 3 squared is 9, minus 9 gives us 0. Hypothesis is satisfied, but the conclusion is false. Negative 3 does not equal 3. And so for this value, for x equals negative 3, this is a false statement. So the first one was true, hypothesis and conclusion were satisfied, and this one, hypothesis satisfied, conclusion is false, so the implication is false. So this one's not true for all x. It turns out that negative 3 is the only thing that breaks this, since that's the only other way to make the hypothesis true. All right, so let's look at another related thing. That's the converse is just switching the order. The contrapositive involves some negations. So the contrapositive of the implication is the open sentence. If x squared minus 9 is not equal to 0, then x is not equal to 3. So notice here we're starting with the x squared minus 9 thing, but this is the negation of that. So x squared minus 9 not equal to 0 is the negation of Q of x. and then x not equal to 3, that's the negation of p of x. So this would be the statement not q of x, or rather the open sentence, not q of x implies not p of x. Now the implication itself was true for all x. That always worked. And in fact, the contrapositive is also going to be true for all x. Let's see why that makes sense. If x squared minus 9 is not equal to 0, so the only way to satisfy that is if x is not 3 and x is not negative 3. And so then, necessarily, x won't be equal to 3. Right? The only way to make the hypothesis true is if x is not equal to 3 and x is not equal to negative 3, and so it must follow then that x is not equal to 3. We just said that in words. And so this is also true for all x. Now that's not a coincidence that the implication and its contrapositive have the same truth value for every single x here. In fact, the implication and its contrapositive always share the same truth values. These are equivalent statements. So let's take a look at a truth table to see this. I'll go ahead and list all of my possible combinations of component statements. True, true. True, false. False, true. False, false. So the implication P implies Q is true here. False here. Since the hypothesis is satisfied, the conclusion doesn't follow. Here it's true, and here it's true, since the hypothesis is false. Q implies P, I'm going the other direction. So true implies true, that's true. So now Q is the hypothesis, so false implies true. Hypothesis is not satisfied, and so the implication is necessarily true. In this third row, the hypothesis Q is satisfied, but the conclusion is false. So this would make the implication false. And lastly, we have false, false, and in this case, Q implies P would be true. So that's what the column would look like for the converse of the implication P implies Q. Lastly, we'll compute not Q implies not P. So even though we have not Q and not P, I might have made a column for not Q and a column for not P. I'm just going to do this in my head, and that's okay to do. So not Q implies not P. So not Q would be false here, and not P would be false. So here the hypothesis was false. Right now the hypothesis is not Q, and the conclusion is not P. So hypothesis is false, and so the implication is true. Here the hypothesis would be true, right? Not Q is true. And the conclusion not P is false, and so that would be false. Not Q would be false, not P would be true. So that would be the hypothesis is false, and so the implication is true. And then here, not Q would be true, so the hypothesis is satisfied, so we better see that not P is also true, and it is. P is false, so not P is true, and so the hypothesis implies the conclusion. And so we can see here, no matter what P and Q are, right, this is true for any two statements P and Q, that this column, P implies Q, is always the same as this column, not Q implies not P. And so these two statements, the implication P implies Q, is equivalent to the statement not Q implies not P. We can also see from this that the original implication P implies Q is not always the same as the converse Q implies P, but it is always the same as its contrapositive. One thing that's going to crop up a lot is a need to negate an implication. So how do we negate an implication? What statement comes out of that? We know that we can just negate the implication But actually what we're going to do here in order to figure out what the negation should be is we're going to first find an equivalent statement to P implies Q. We're going to write that using a disjunction. So this is pretty incredible that we don't actually, oops, I'm going to use red. We don't actually need to use an implication symbol to state an implication. So here I'll first just list the possibilities. And then evaluate P implies Q, true, false, true, true. Evaluate not P, false, false, true, true. And then over here I'll compute not P or Q. So I'm looking at the not P column and the Q column. In this case Q is true, so it's true. They're both false here, so this is false. And then here they're both true, and here not P is true. So this is pretty cool. P implies Q, that column, is the same thing as not P or Q. That these are really saying the same thing. So think about this in this example we've been using. If you cross the Mackinac Bridge, then you pay $5. So what I'm claiming here is that this, another way to say this would be, so remember P is if you cross the Mackinac Bridge, and Q is you pay $5. So this is P, you pay $5 is Q. So this is the same thing as saying you don't cross the Mackinac Bridge or you pay $5. But that's really saying the same thing of if you cross the Mackinac Bridge, then you pay $5. Either you don't cross the Mackinac Bridge or you pay $5. So we haven't negated anything yet, not really. But we have identified that P implies Q is the same thing as not P or Q. Now, this is really useful to state an implication using a disjunction and a negation, because now we can apply some laws of logic to figure out what the negation of P implies Q should be. So let's take a look at, let's figure out what's the negation of P implies Q. So this, by what we just found above, is the same thing as not P or Q, so just rewriting it using what we have above. And now I can use De Morgan's law to distribute this negation through. So this would be not P or not Q. Not P, we know we can use double negation there. That's P. Sorry, I made a mistake, didn't I? This should be an and. Hopefully you caught that. Remember, when we negate a disjunction, it turns into a conjunction. It switches negation to, or disjunction to conjunction and conjunction to disjunction. So this is not P and not Q. So this is P and not Q. So let me write this down in one line. Not P implies Q is the same thing as P and not Q. Now let's think about this really quickly with our example. If you cross the Mackinac Bridge, then you pay $5. If I wanted to prove that this thing is false, if I want to prove that this implication is not true, well, how would one do that? How would one show that this implication isn't true? I claim if you cross the Mackinac Bridge, then you pay $5. If you want to prove me wrong, well, what you would have to do is you'd have to cross the Mackinac Bridge and not pay $5. That is P and not Q. So proving this implication wrong, that's the same thing as the negation of it. That's P and not Q. And so that's how we can reason through that this really does make sense for the negation of an implication, and we can use the laws of logic to prove that. And so this guy right here, we will use a lot in this class. There's going to be many cases where we want to prove that an implication is false, or assume that an implication is false and show something else has to happen. And so in order to do that, in order to make sense of that, we'll have to negate it and express it as P and not Q. That'll be really useful for us later on. The last thing I want to talk about involved with implications is the idea of a biconditional. So a biconditional is really just the conjunction between an implication and its converse. So if we take an implication, so I'll write the implication here, P implies Q, and its converse, Q implies P, then the biconditional of P and Q, biconditional, is P if and only if Q. And that's how we say that. We could say either the biconditional of P and Q, or we could say P if and only if Q. Why can we say P if and only if Q? Remember that P implies Q is the same thing as saying P only if Q. And Q implies P. We could say that by saying P if Q. Remember those equivalent ways to state an implication. And so when you take the conjunction of those, we get P only if Q and P if Q. That is P if and only if Q. And we write that P if and only if, and that if and only if, we just use notation IFF. So that extra F is for only if, not a typo when I draw two F's for an if. It actually means a biconditional. So that's what a biconditional is. Let's look at the truth table for it. So I'll go ahead and fill in these combinations of truth values. True, false. False, true. False, false. This should be getting tedious by now. P implies Q, that's true here. False here. True here. And true here. Q implies P. True here. True here. False here. And true here. So P if and only if Q, this is right, this is a conjunction of P implies Q and Q implies P. So I'll look at the P implies Q column and the Q implies P column and do an and statement on those. So I get true for that. Here P implies Q is false, so that makes the conjunction false. Here Q implies P is false, so the conjunction is false. And then down here they're both true, and so the conjunction is true, and so the biconditional is true. So I want you to notice something with this, is that when is the biconditional true? Well, that's only true when P and Q share the same truth value. That's the only way to make the biconditional true, is if both P and Q share the same truth value. That's sort of an equivalent way to think of a biconditional. So let's go ahead and look at an example. I'll give you these three open sentences where X is a real number. And we'll just go through a couple different biconditionals involving these and figure out when they're true. So P of X if and only if Q of X. X equals 3 if and only if X squared minus 9 equals 0. So here we have a compound open sentence. So we'll want to look at our component open sentences and see what makes those true. So P of X is true when X is 3. That's the only way to make that true. That one's pretty obvious. X squared minus 9 equals 0. Well, for that we need X to equal 3 or X equals negative 3. That's the only way to make Q of X true. So let's just take a look at this biconditional in a couple cases. So let's just plug 3 in. P of 3 if and only if Q of 3. So this would be the statement 3 equals 3 if and only if 3 squared minus 9 equals 0. In this case, P and Q have the same truth value. They're both true. And so in this case, the biconditional would be true. We'll look at one other case. What if we look at a couple other ones. Let's say P of 0 if and only if Q of 0. In this case, P of 0 is false and Q of 0 is false, and so the biconditional here would be false. So that would be sort of like the last, and then the biconditional would be true in this case, right? If they're both false, then there's no condition satisfied. That makes a biconditional true. That's the last row of the definition of the biconditional. But we could also have a situation like P of negative 3 if and only if q of negative 3. So in this case, negative 3 does not equal 3, so p of negative 3 would be false, and q of negative 3 would be true, right? Negative 3 squared minus 9 is equal to 0. So in that case, they don't share the same truth value, and so this would be false. Turns out that for all other values of x, this biconditional is true, that negative 3 is really the only thing that breaks it. In all other cases, p and q are going to share the same truth value. Well, let's take a look instead at q of x if and only if r of x. So we can try some similar things. Q of 3 if and only if p of 3. And so this would be saying, so r of 3. So r of 3 is the statement 3 equals 3 or 3 equals negative 3. Well, 3 does equal 3, so r of 3 is true, and q of 3 is also true. And so this would be true in that case. And remember, negative 3 was the problem last time, but this way, you see how we included more things in our condition in r of x, right? We did not just x equals 3, but also or x equals negative 3. And so let's see what happens when we evaluate this at negative 3. Q of negative 3 if and only if p of negative 3. So in this case, again, r, I keep saying p. R of negative 3, x equals negative 3 equals 3, that's false. Or negative 3 equals negative 3, that's true. So r of negative 3 is true, and q of negative 3 is true. So they share the same truth value there. So the biconditional is true here. And if we try anything else besides 3 or negative 3, well then r of that thing will be false, since it's not 3 or negative 3. And q of that thing will also be false, because the only thing that makes q true is if x is 3 or x is negative 3. So in any other situation, both r and q would be false, and so the biconditional would be true there. So actually, q of x if and only if r of x is true for all integers, or for all real numbers x. So this is the idea of a biconditional. Remember that this means that the two things have to have the same truth value. It could be true or it could be false. As long as they have the same one, the biconditional is true, and that this is really a conjunction of an implication and its converse. All right, that's it for this one.